Okay, so this is where we left in the last location. We have to, in the last location, so we have orthoamphiboles forming grunerite and gedrite. And then you have clinoamphiboles. These are monoclinic amphiboles. And they can be described by several phase compounds. These are the magnesium in member components. These are the iron in member components. So you can conceive tremolite, magnesium-adenite, magnesium-pergosite, and magnesium-shematite, and the corresponding iron in member forming what we call essentially is hornblende amphiboles. Hornblende. Now, these hornblendes, as you can see, this hornblende here. I will just put a red mark here. Yes, this hornblende, tremolite, actinolite, these have no aluminium in their crystallographic sites, right? So they are called non-aluminous or subaluminous amphiboles. But these are more aluminium-rich amphiboles. What increases, you see, as you grow from here to here, the aluminium by silicon ratio here is 4/6, it's 3/6, it's 1/7, and here there is no aluminium. So essentially, this is how the aluminium by silicon ratio changes. The other thing is, this is also the ratio, you see, in all of these amphiboles, calcium is 2. If you calculate the stoichiometry based on 22 oxygen and 2 OH radical, or if you remember, we did it in the lab class, if you take out H2O, if you take out H2O from this, there are 23 oxygens. So if you calculate on the basis of 23 oxygens or 22 oxygen and 2 OH radicals, then calcium is 2 in all these clinoamphiboles. Now here you will see Ca is to Reg ratio is 2:5, 2:5, 2:4, 2:3. Calcium by magnesium ratio increases as we move downwards. And all these components can be derived from tremolite from orthoamphibole to tremolite by replacing magnesium iron, 2 magnesium iron by 2 calcium. Here, one of the silicons is changed by sodium and aluminium. Here, from the last one, silicon plus magnesium is aluminium plus aluminium, and then sodium plus magnesium gives you aluminium. These are the different substitution schemes that are available for the amphiboles. And as I said before, I've eliminated all amphiboles with titanite, ferric iron, potassium. I have neglected all this. These are generally the more common amphibole assemblages. Right. Now, what we do is, you also remember the ionic radius, isn't it? You also remember the ionic radius. So when you talk about aluminium-rich amphiboles and aluminium-poor amphiboles, you would expect, remember how are these done? These aluminium are coming in because of replacing magnesium plus silicon. Essentially, that is what you're replacing. Magnesium plus silicon by aluminium. So you can imagine that aluminium ionic radius and silicon with magnesium ionic radius are not one and the same. So there will be differences, and therefore these replacements might tend to give you some sort of what is called an immiscibility gap between the two. Now, I will not be talking further about orthoamphiboles. We will talk more about clinoamphiboles. And I will draw a diagram which will help you to conceive it. So remember all this. These formulas are important and you should remember it. It's not that you have to remember. If you remember NG7, you can derive the rest, remembering how to do it. Right? So now, let us let me now make this different amphibole components into some sort of a composition space, and let's see how this works. Let me first draw the diagram. It's a little tricky. Let's imagine this block here. And let me write down the first one, Ca2 Mg5, Ca2 Fe5. Now what did I write? Here, this was tremolite and this was actinolite. What was the substitution scheme? Magnesium being replaced by iron. So this is where you have tremolite and this is where you have actinolite. Then here we write Na. I will keep this blank here, indicating that this is a vacancy. And so now you have NaCa2 Mg5 Al Si7. Remember, this was Si8 and this was Si8. O22OH twice is common. So here we have NaCa2 Mg5 Al Si7, and of course you can imagine if we do the iron end member, NaCa2 Fe5 Al Si7. So this is what we call magnetioadenite, and this is called ferroadenite. And the substitution scheme, as you can see here, is silicon 4 plus being replaced by Na plus plus Al3 plus. That's the substitution scheme. And if we do this, then we continue with this here. NaCa2 Mg4 Al Al2 Si6. This will be another component here. You can see this is magnetiopargasite. This is magnetiopargasite, and you have NaCa2 Mg4 Al Al2 Si6. That's ferropargasite. And what is the replacement here? The replacement is magnesium plus silicon replaces aluminium tetrahedral plus aluminium octahedral. This is the replacement.
So this will be a Fe.
Hi, Fe4. And now we are left with the Sherbakite. So there you have blank, sodium goes off, and you have Ca2 and then Mg3, Al2, Al2, Si6. This is magnesium Sherbakite, and this one here is Ca2, Fe3, Al2, and you have Al2, Si6. This is ferro-sherbakite. So all the components that were important for us are now taken into this compositional block, where this is the Covingtonite series, then you have the Edenite series, then you have the Pergasite series, and then you have the Sherbakite series. So each of these have constitute one of the series. And your hornblende essentially lies in the volume of this composition diagram. So you have Covingtonite series, Edenite series, Pergasite series, and the Sherbakite series. And your amphibole lies in the composition space included within this. What are the boundaries? Very quickly, if you have missed it, if you see this plane in front of you, I will try and see if I can put some colors so that you understand it better. This plane in front of you. This one. It's an iron plane. So this plane in front of you is iron. There's no magnesium. Whereas the plane behind is magnesium. So the plane, the side behind you, behind this parallelogram is magnesium. And on the front of it, you have iron. Similarly, if you look at this part of the diagram, this here is no aluminium. No aluminium. And if you take this and this, this and this and this, both have Fe5, Mg5. So the magnesium-calcium ratio does not change on this plane. But if you go here on this plane, here you can see iron and magnesium are higher. So from this side to this side, aluminium by silicon ratio increases. From the back to the front, Fe increases, or you become more iron rich. So this is the parallelogram for the clinoamphiboles. Now I will first let me draw a plane and then we will discuss it. I will draw it with a wet pen. This plane. Can you see that? It's a little above actinolite, tremolite, these 2 points. And this is about Sherbakite, Pergasite, roughly 50-50. This point, say for example, if we ask you, this is Pergasite and this is Sherbakite, roughly around 50-50. And this one, very dominantly actinolite rich, but a little bit of Edenite component. And this is where the boundary is, this plane. Now what is this plane? Why did I draw it at all? The answer to this question is, if you take metamorphic rocks from all over the world, what they will do is they plot roughly on this plane, above and below, But this is a wonderful median plane where all the amphiboles in metamorphic rocks plot. All amphiboles in the metamorphic rocks fall. That is the important thing. So it is the plane of naturally occurring amphiboles in metamorphic rocks. But there are slight differences. Say, for example, if you plot the low-grade green schist facies amphiboles, clinoamphiboles, green schist facies clinoamphiboles, they would plot somewhere here. Do you understand? If you take the green schist facies amphiboles, they will plot somewhere here. But if you plot the granulite facies or the amphibolite facies amphibole, they will plot somewhere here. These will be the plots of amphibolite to granulite facies amphiboles, even eclogite facies amphiboles. And if you plot the green schist facies amphiboles, they would roughly plot here. But some of the epidote amphibolite facies assemblages, they plot like this. They plot like this. So what happens is, plot like this, they don't plot right across the middle. It is because there is here a solus. There is here an immiscibility gap. There is an immiscibility gap. So the high-grade rocks, amphibolite, granulite, eclogite, they tend to plot, as you take granulite for example, they will tend to plot mostly as the adonite pergosite on this side, the green schist facies rock on this side, the epidote amphibolite faces a little bit here, but generally there is a gap of amphiboles, and this causes the immiscibility gap in amphiboles, where you have low aluminium amphiboles. This is here, you can see low aluminium amphiboles. This is high aluminium amphiboles. And this is where you have two amphibole assemblages. Remember, we are talking of clinoamphiboles only. So you have high aluminium amphiboles. You have two amphibole systems here. Why two amphiboles? Because the miscibility gap is like this. Miscibility gap is like this. So if you have a composition somewhere here, it will split into a high aluminium amphibole and a low aluminium amphibole. So you will have two coexisting amphiboles. And this is typical of the epidote amphibolite facies. And in the green schist facies, you have low aluminium amphiboles. This is what is called tremolite actinolites are stable in the green schist facies. That is why when I gave you the list yesterday, we were talking of actinolite bases. So essentially, actinolite facies amphiboles like plot here of the green schist facies. But the granulite facies amphibole would plot at this aluminium rich end of this material, of this plot. And in between, you have the two miscibility amphiboles. This is the way to understand clinoamphiboles, not Barkevicite, Rebekite, Kersutite. Those amphiboles are all very extraneous amphiboles, containing titanium, ferric iron, potassium. We are not going into that. But generally, this is the distribution. It's a very good diagram to remember what's happening. And if you say the metamorphic grade the metamorphic grade. We know that the metamorphic grade, with metamorphic grade, the aluminium content of amphibole increases. But what about the MgFe? See, in the front you have Fe, on the back you have Mg. What is the MgFe? Normally the diagram shows that your trajectory is roughly like this. That means your amphiboles are low aluminium Fe-rich amphiboles in the metamorphic rocks. But as you go to higher metamorphic grades, your magnesium by iron of the amphibole increases slightly. Okay? So with metamorphic grade, magnesium, you can see magnesium with respect to calcium increases, with respect to calcium decreases, aluminium by silicon ratio increases, and iron by magnesium ratio decreases as we go to the highest grade. So one of our discussions, which we will do later, is why this happens. And if you remember my lecture from last lecture, you would remember this has also got to do something with calcification of plagioclase. This is also to do something with plagioclase. Because if you remember in the diagram in the talk that I gave you, the last video lecture, I was talking of albite in the Vinci phases, albite oligoclase in the epidote amphibolite phases, and then oligoclase andesine in the amphibolite phases, and amsdesine in the granulite phases. So that is very important. So you see, when you make a, say for example, when you take a plagioclase, and you write albite, that means NaAlSi3O8, and then anorthite, which is CaAl2Si2O8. You can see two things here. When you move from albite to anorthite, in between you have albite, oligoclase, andesine, bitonite, labradorite. Aluminium by silicon decreases. Aluminium by silicon decreases. Here it is, increases. Here it is 1:3, here it is 1:1. Aluminium by silicon increases. So also in the amphiboles, aluminium by silicon increases. Also here you will see, if you become calcification of plagioclase, Ca by Na will increase at increasing metamorphic rate. Ca by Na in plagioclase will increase. Here, of course, it's not a problem, but you can see here you have more Na, you're moving into more Na-rich amphiboles as you go to the highest metamorphic rate. These needs to be explained, and which we will do later on. So, say for example then, if I take this plane, say I tell you I have a hornblende, with this composition, tremolite 3, edenite 7, pergosite 50, schermakite 40. You can see tremolite, edenite, pergosite and schermakite. If I take this, then obviously you can see these are the dominant. Pergosite, schermakite dominant. So this means this amphibole comes from the epidote amphibolite or from the granulite phases. But if I tell you that there is an amphibole where tremolite is 85, edenite 10, pergosite 2, schermakite 3, you know this is a low temperature amphibole. So this type of amphibole cannot be stable in the granulite phases. This amphibole would be stabilized in the granulite phases. This would plot somewhere here, and this amphibole would put somewhere here. So that is the problem. From looking at the composition, if you fragment it in terms of tremolite, edenite, pergosite, and schermakite, you will be able to say which metamorphic grade are we talking to. Okay, now as I told you in the last class, we will first talk on the breakdown of amphibole. You know amphibole, the assemblage characteristic of the amphibolite fascies is amphibole plagioclase quartz. This is the characteristic assemblage. Amphibole plagioclase quartz is the classic example of epidote amphibolite fascies. At higher metamorphic grades, what you will get? Garnet. At higher temperature, you will get clinopyroxene. So if you have a box, epidote amphibolite, amphibolite fascies, you will have amphibole plagioclase quartz. That's a classic assemblage. As you move to higher pressure, the chances are you will get garnet. And if you move to higher temperature and higher pressure, the chances are you will get clinopyroxene. So that's what is about amphibolite fascies. So, and as you move further right of the amphibolite fascies, you get granulite, and this is marked by the incoming of a classic mineral orthopyroxene. Right? So we will talk about this boundary today based on an amphibole. Have you understood? Which amphibole we will talk about? Is it this amphibole or is it this amphibole? The answer is we will not take this amphibole. Why? Because that's the amphibole of the richest phases that has undergone compositional changes. So we will take such an amphibole to see what happens at the amphibolite granulite fascies boundary. Just give me a little time. So this is what is called amphibole composition space. If you remember it, it would be wonderful. You can derive it. There is, if you know the substitutions, you should remember it. I told you that there are several other solid solution phases like chloride, etc. Also plagioclase. We will talk about that a little later. But the moment here is, before we start, I will just tell you, say for example, you have the amphibolite fascies, and you have the granulite fascies. And if you take the mafic crux, classic assemblage, hornblende, plagioclase, plus minus quartz, plus minus garnet, plus minus clinopyroxene. This is the classic assemblage. But hornblende plagioclase quartz is classic. Plus minus quartz is classic. Garnet slightly high pressure, clinopyroxene slightly high temperature. And then you have the granulite fascies. And here the major mineral that comes in is orthopyroxene. And then you have plagioclase. And then you have quartz, plus minus clinopyroxene, plus minus hornblende, plus minus garnet. Again, this classic assemblage. Orthopyroxene, plagioclase, quartz, plus minus clinopyroxene, plus minus hornblende, and plus minus garnet. You see garnet, hornblende, and clinopyroxene, garnet, hornblende. They are present in both. Similarly, plagioclase and quartz are present in both. So the mineral that we have to account for is orthopyroxene. That is the mineral that we have to account for when you are crossing over from amphibolite fascies to the granulite fascies. And we will see how this works. And for that, we will take an assemblage I did a calculation myself, so I will just take that, but you can choose another synthetic analysis. I took an amphibole analysis, tremolite 3, edenite 7, pergosite 50, and schermikite 40. That was my composition. In terms of mole fraction, this is on mole percent. This is mole percent. But if I do to mole fraction, this will be 0.03, 0.07, 0.5 and 0.4. That should be in terms of mole fraction. But here I am talking of mole percentage. Now what we do is that these are the three components. We at the moment ignore magnesium-iron ratios. Magnesium-iron ratios we ignore, we assume them to be one and the same. So let's say we are trying to explain the appearance of orthopyroxene. We are trying to explain the existence of orthopyroxene. So first we take, if we take trebolite, so we take Ca2, Mg5, we ignore iron, Si8, O22, OH2 twice. And then you, at the higher temperature, what you will break down into, as you can see, you can break down into CaMg Si2O6. That's pyroxene. Then 3Mg SiO3, that's orthopyroxene. Then 2 into 2, 4, 4 and 3, silicon 7, here it is 8 silicon, so plus SiO2 and plus H2O. So what you get here is 2 pyroxene assemblages and you have quartz as a product phase. You product quartz as a product phase. Now let's say we take adenite. And then we have Na, Ca2, Mg5, Al, Si7, O22, OH2 twice. And this we now break it down. So you see the mineral that can accommodate sodium would be albite. And albite has NaAl Si3OA. So if I take Na, this Al also goes. So you have NaAl Si3O8. Right? Then you have no extra aluminium left, because for every Na, one aluminium is taken away. So NaAl Si3O8. And then you have 2Ca Mg Si2O6 plus 2 Mg is gone, so you're left with 3. So it is 3 Mg SiO3 plus H2O. Now let's check water, silicon. Here it is 3, 2 into 2, 4, 7 plus 3, 2 into 2, 4 plus 3, 7 plus 3, 10. And here you have 7. So this is plus 3 SiO2. Now here quartz is a product. Sorry, 3 SiO2 is a reactant. The important point, you have to note this important point. Here, the 2 pyroxene assemblage, this is clinopyroxene and this is orthopyroxene. It's in the ratio 2:3. Right? Here also, if you see the 2 pyroxene assemblage, it is in the ratio 2:3 mole percent. Right? And now you get NaL Si3O8, that means plagioclase is produced, but that plagioclase is albite 100. The plagioclase is albite 100 because there is no Cal to Si2O8. So albite means plagioclase is albite 100. You produce a pure albite along with 2 pyroxene assemblages. Then we take pargasite. So now we have Na, Ca2, Mg4, Al, Al2, Si7, O22, OH2 twice, and we start the breakdown reaction. Here you can see as before we have NaL Si3O8. So NaAl Si3O8. But After taking Na and one of the aluminium goes, you still have 2 aluminium left. So now you have to take into aluminium, and the only way you can take it is CaAl2Si2O8. Have you understood? So 2 aluminium plus 1 aluminium, 3 aluminium. Here there are 3 aluminium, it's gone, but you have taken only 1 calcium, so 1 calcium is left. And this you can write as CaMgSi2O6. So you have taken 1 magnesium, but you have 4 magnesiums here. So you have to take 3 MgSiO3 plus, of course, H2O. And now if you look at silicon, so silicon is 3 here, plus 2, 5, plus 2, 7, plus 3, 10, and you have 7 here. So this should be plus 3 SiO2. Just let me check if I am correct. So it is 3 plus 2, 5, plus 2, 7, plus 3, 10. Here you have, oh, there you go. I made a mistake. Si6. This should be 4. Al2Si6 it should be. It's not Si7 because this term always has 8. So Al2Si6, it also has to be 8. So this is the breakdown reaction. Once again, quartz is a reactant. And you have a plagioclase now where there is 1 mole of albite and 1 mole of anorthite, and this would make albite 50. This would make it albite 50. NaLSi3O8, Cl2Si2O2, 1:1 mole proportion, so albite should be 50. So if you are taking a pergasite, you again produce 2 pyroxide assemblages. 1:3 now, 1:3. This is 2:3. This is 2:3. So you can see the proportion of 2 pyroxide assemblage, molar proportion changes, and the composition of the plagioclase that is produced also changes. So what you are saying here is, depending on the composition of the amphibole, your products are also changing. And then you go into sherbakite. So now we go back to the blank, and we have Ca2, and then Mg3Al2, and then Al2Si6, O22OHO twice, plus, and then we have this expression. Now, sherbakite, what will you do? There is no sodium, so you don't have to worry about sodium. But you have to take into account aluminium. And there are 2 plus 2, 4 aluminiums. But you have also 2 calcium. So what you do is, you produce 2 CaL2Si2O8. 2.5 pounds. And you have taken care of calcium and aluminium, both. There is no more aluminium left, there is no more calcium left. So you will not be producing a clinopyroxene at all. So the rest of it has to go as 3MgSiO3. So now we have plus H2O. So if we look at this, then we have silicon. It is 2 into 2, 4 silicon, plus 3 silicon, 7 silicon, and here you have 6 silicon, so it should be plus SiO2. But this now has created a problem. So you have an anorthite, so this is albite 0 now, because you have produced a pure anorthite. So albite is 0, and there is no clinopyroxene. No clinopyroxene. So you can see, depending upon which component is more or less, your reaction products are completely changing, which is in terms of the presence or absence of pyroxenes. Presence or absence of pyroxenes. their proportion of pyroxenes and the composition of plagiaries. And the composition of plagiaries. That's what it is. So this is very important to realize here. That depending on the composition of the amphibole, its breakdown product of pyroxene-bearing assemblages, orthopyroxene bearing assemblages, the proportion of the two pyroxenes that is produced, whether orthopyroxene and clinopyroxene will produce, and the composition of plagioclase would change dramatically. Now then, before we go into more details, say for example, if this was my hornblende, it's an important question. I have done a little bit of calculation, but I want you to check it also, whether my calculations are right. So user, as I said, when you listen to my video lectures, you take a book and keep next to it and try to do the calculations again, or try to do another thing and try to do it differently. And you're seeing that in the text I don't give copybook questions. It's no use, because I have taught it, you have the lecture notes, you have your friends. So we will have in the last exam questions which are a little bit, you cannot get it from anybody. But if you're thinking and if you're studying, you should be able to get it. It's not beyond your logic. Okay? So now, if this is my composition of the amphibole, what is the composition of my hornblende? What is the composition of my hornblende? How will I do it? Say for example, I have this side. You see, okay. If I have to find out the composition of the hornblende, say for example, I want to find out how much sodium is there in the hornblende, in the amphibole, which is tremolite 3, adenite 7, pargasite 5, tremokite 40. How will I find my sodium? Say here, adenite, sodium then should be multiplied by 0.07 into 1 plus 0.5 into 1. This is how much is your sodium. Why? Adenite, mole fraction is 0.07. So 0.07, I will put this under bracket, it's better. 0.07 into 1 plus 0.5 into 1, and that will be the sodium content. So your sodium essentially will be equal to sodium 0.57. That will be your sodium. Have you understood? Now, what will be calcium? I will do it, but then I will tell you how stupid we were. So calcium, you can see what is here, calcium 2 into, or the same way, 0.03 into 2 plus 0.07 into 2 plus 0.5 into 2 plus 0.4 into 2. Isn't it? So you take 2 common and you will end up with 1. 2 into 1 is 2. Of course, because in every formula it's 2. So calcium will turn out to be 2. So that will be my calcium. Okay, then let's go to aluminium, you see here. Let's go to magnesium and see what happens. Magnesium. So, magnesium, once again you try with tremolite, 0.03 into 5 plus 0.07 into 5 plus 0.5 into 4 plus 0.4 into 4. That's magnesium. Right? And this value comes to...
So that's 3.
Which one?
Shamalite. Mg3.
Yes, yes, yes. Can you tell me how much it comes to? This will be 0.15, this will be 0.35, this will be 2.0, and this will be 1.2. This is how it will be. So 2.0 plus 1.2, 3.2, 3.2 plus 0.25 is 3.55 plus 0.15 is 3.70. 3.70. Is that right? Just check it out. 3.7.
Yes, 3.7.
So magnesium is 3.7. Right? So now sodium is 0.7, calcium is 2, magnesium is 3.7 for the full amphibole. Now we talk about ale octahedral. So ale octahedral means this term. Ale octahedral. So what will be the value? The value will be for the first term, there is no aluminium octahedral. So there is no value for that. Second term, there is no aluminium octahedral, no value for that. Aluminium octahedral comes in here. So what will you do? 0.5 into 1, 0.5 into 1 plus 0.4 into 0.4 into 2. So aluminium octahedral becomes, this is 0.5 and this is 0.8. So it is 1.3. So we have aluminium in the octahedral site is 1.3. Now you see here, interesting. Magnesium in the octahedral site is 3.7. Aluminium in the octahedral site is 1.3. You add up the two, it becomes 5. That is what it is. The octahedral sites, all I have to find. Of course, I could have just taken aluminium octahedral and subtracted it from 5 minus 3.7 and I would have got 1.3. But I just wanted to do so that you get a hint of it. Okay, so now we go into aluminium tetrahedral. Aluminium tetrahedral sites. So aluminium tetrahedral, there is no aluminium here. We don't need to get bothered. Aluminium tetrahedral comes in here. Remember, there are total 8. 8 silicon, 8 here, 8 here, 8 here. So the total is 8. So we now come to aluminium tetrahedral. This one is 0. So we come to 0.07 into 1. 0.07 into 1 plus. Here it's 2. 0.5 into 2 plus 0.4 into 2. So this will be 0.07, this will be 1.0, this will be 0.8. So it will be 1.87. Is that right?
Yes.
Aluminium octahedral is 1.87. So what should be our silicon? 8 minus 1.87. That means 6.13 should be our value. Let us check. Silicon tetrahedral. Silicon tetrahedral. Remember the value I said? It should be 8. It should be 8 minus 1.87. That means 6.13 it should be. There's no escape route. So silicon tetrahedral. So how is it here? 0.03 into 8 plus 0.07 into 7 plus 0.5 into 6 plus 0.4 into 6. That's how it is. So this is 0.24. This is 0.49. This is 3.0 and this is 2.4. So if you do that, so it's 3.0 plus 2.4, 5.4, 5.4 plus 0.49, 5.89, 5.89 plus 0.24 is 6.13. So silicon tetrahedral is 6.13. So my formula, eventual formula of the Hornblende is sodium 0.57, calcium 2, magnesium 3.7, aluminium octahedral 1.3, aluminium tetrahedral 1.87, 1.87, silicon 6.13, O22 OHO twice. That's the composition of my amphibole. If the amphibole could be split into this. In the next class we will talk about what are the proportion of the product. Have you understood? This is the composition of my Hornblende. Right. Thank you. We will do it in the next class.